And this is the algorithm of policy iteration. This is written like this. It is written in 3 stages. The first stage is only the initialization, so you start or you create your table for the values of the states, and you give them real values, real numbers, so it could be 0. And then you start creating the policy that you will be evaluating, and what they tell you to do is to assign to each of the states. So if you have 3 states, you will assign to each of these states one of the possible actions, and you will do that arbitrarily. Okay, so here in this step you will say, okay, for state 1 I will assign action go right, for example, and for state 2 I will assign action go left, and for state 3 I will assign action go right. So arbitrarily, randomly, you just assign an action, a possible action, to this policy. So as you can see here, this policy now, the way we are using it, is not a probability distribution, but it's just a mapping. It's going to tell you, it's a deterministic function in this case, and this is going to tell you if you are in this state, just apply this action. So once you have initialized these 2 elements, the value function and the policy function, you go to stage 2, which is policy evaluation. Okay, stage 3 is policy improvement. So we are going to apply step 2 and step 3 iteratively until the value function has been estimated. So policy evaluation, again we have this delta to stop this loop here, this main loop here, repeat. And let's go directly to the rule. The rule says you will give, or you will update the value of one of the states as the sum for every possible next state of these products here, which is the transition probabilities. And here you have again the reward and the discounted value of the next state, S prime. So again, consider if S prime could be any of your possible states. So if you have 3 states, you need to consider here 3 terms, 1 term for each of the states, S prime. And here you will consider the policy that you assigned initially, which is a random policy. Remember, each of the states here, you will assign a random action. So you will compute that probability for that action also here, and the value that is the result of this expression, that's going to be the next value for that state. You need to apply this for every state, so for state 1, 2 and 3, and you will be keeping track of this difference. When you consider that this is enough, so it is very small, this change from one state to the other, from one iteration to the other, then you stop this. So after this part has converged, has stopped, you have performed policy evaluation. Then you need to go to step 3 or stage 3, where is policy improvement. So you have updated your value according to this policy. So the first time you run this, you will update your value function based on a randomly generated policy. Okay, but that's okay, it's the first time you apply this. When you go here, then you will update your policy, the one that is randomly jet. So you will say, okay, now I want to look for the best action that I can perform for each one of the states. So for each of the states, you will check which of the actions is the best one, is the action that will maximize this expression here. And this expression here is basically the same here. So you will compute that, and then you will update. If there is an action that has a largest value, is better than the previous one, then you will replace that. So maybe initially we said that this this action for state 1 was going right, but then I don't know, the action well, in this case maybe it is the same to go right, but if we were initialize this like with action go left, and we know that for that example going right is the correct one, then you will replace, and now the best action for state 1 will be go right. So that's the idea here, that you will improve this policy based on the current knowledge that you have from the values. When you see that you haven't updated the policy, so if you notice that you haven't changed the actions assigned to each of the states, then you will consider that the policy is stable. Okay, and then you will check here if the policy is stable, then you stop. If the policy is not stable, so at least one of the states changed the best action, then you need to go again to policy evaluation. You update the values for every state, so you perform policy evaluation, and then you go again to policy improvement. You update the policy and check again. If there are changes, it is unstable yet, you need to go back to policy evaluation, update the value function, and go to policy improvement. If you check that now there was no change in the policy, then the policy is stable, and then you stop. So this is the second algorithm. This is called policy iteration. The first one is called iterative policy iteration. Now, the third algorithm is called value iteration. Recall that the default policy evaluation backup involves using these two sums here. The first one is over all possible actions. The second one is over all possible next states, S prime. Okay. Here in value iteration, we won't use this sum for every possible action. We will go directly and we will update the value for the next iteration, considering the action that maximizes this expression. So this is similar to the previous one, to the previous algorithm, but instead of having two stages, instead of having policy evaluation and policy improvement, here we will assign the value directly that maximizes this expression, considering each possible action. So the result of that is that in only one stage, in only one loop, every time you update the value for one state, you simply compute or you search for the action that gives you the largest result here in this expression. And once you have found that action, you need to update the value function with the result of this expression for that action. Okay, so basically you will assign the next value for that state, considering only the best action from that state, and the best action is the one that maximizes this expression. This is called value iteration, and is the last algorithm that we study in this chapter. Once the algorithm has converged, so the delta is very small according to your theta, you stop, and then you simply output as the policy, the best policy to behave in that environment, as the argument or the action that maximizes this. So you simply check for every state what is the best action, what is the action that maximizes this expression, and you assign it to the policy. And then you just if you apply this for a robot that learned to perform a task, then this is the knowledge that your robot will have, and you will need to let the robot use this function to move around its environment. So this is the knowledge final. It's the policy, the behavior policy, the optimal behavior policy. Now, these three algorithms are similar, or let's say they get to the same values for the states, for all the states. So they are equivalent in terms of the final solution that you will find. The difference is that some are faster than the others. Like for example here, you can perform this faster than the general, the first one, the iterative policy iteration algorithm. But in terms of the result, you will get to the same result. You will be able to find the optimal policy for your MDP. There is a concept that I talked about it before, which is the asynchronous sweeps, asynchronous DP or dynamic programming. All the DP methods described so far require exhaustive sweeps of the entire state set. So these algorithms require to update the values for each one of the states. Now, asynchronous DP does not use sweeps. Instead, it works like this: repeat until convergence criterion is met, and you will do a pick of a state at random and apply the appropriate backup. So instead of applying these sweeps, these complete sweeps, you will just select randomly states and you will apply the update rule of your algorithm to update the value for that state. So the idea here is that since you are not going to apply this rule to every single state in each of the iterations, then you need an intelligent way to select what are the states that you are going to update and which are not going to be updated. The idea of this is that if you have a very large MDP, an MDP with very many states, and you don't want to run these complete sweeps because it will take a lot of time, so you will just update the values for a subset of states. Now the question, can you select states to backup intelligently? The answer is yes. And the interactions or the way you update these states can give you information that could help you better select these states. So maybe, for example, if you apply this rule to some state repetitively and you notice that that state is not changing the value after some times that you have updated it, then you can say, okay, there's no need to keep updating this state. I will update some other states, because maybe that state is very simple and you have already, with some iterations, you have already estimated the final value for that state. So that could be one way to use the agent's experience to select what are the states that are more important to update. But this is just an example. That could be depending on the problem that you are solving. You can use different criteria to guide the way you select actions to update the value function. So when we do this evaluation and improvement, what we are doing is what we call the generalized policy iteration. Any interaction of the policy evaluation and policy improvement is independent of their granularity, is proof that will converge to the optimal policy and the optimal value. So what you are doing is, in this cycle of evaluation and improvement, every time you evaluate, you improve a bit the value, and every time you do the improvement, the policy improvement, you improve a bit the policy. So you improve both in this cycle, and you will do that up to a point where you finally reach the optimal value and the optimal policy. So this is a generalized policy iteration, and there could be many ways in which you can implement this depending on the properties of the MDP. What we have seen here are the basic or the most simple MDP, where you have finite states, finite actions, and we are studied the basic algorithms in dynamic programming for solving or estimating this policy and this value function. So to find an optimal policy is polynomial in the number of states, but as we have said before, the number of states is often very large. When a MDP has a very large number of states, and the states are given by the dimension of the input or the vector that represents the states, we call this the Bellman course of dimensionality, because this number of states can grow exponentially as you increase the dimension of the problem. The dimension, by dimension I mean, suppose that you are considering the position of a point of part of the robot in a 3D environment. So each position will be determined by 3 coordinates x, y, and z. So that's dimension 3. Okay, but suppose that also, well, you have this for each of the joints of the robot, and suppose that the robot has 20 joints, so that's 3 times 20. We're talking about 60 dimension. So as you increase the dimensions of the variables that you will consider, you will increase exponentially the number of states, and this is called the course of dimensionality. So that's typically the problem in reinforcement learning problems where you have too many states. So in practice, classical dynamic programming can be applied to problems with a few millions of states. Asynchronous dynamic programming can be applied to larger problems and appropriate for parallel computation. So if you want to apply sweeps, complete sweeps, you can tackle even problems with millions of states. But if your MDP is larger than that, then it is better to use asynchronous. And I would say that even with less than millions of states, it is better to apply asynchronous because it is faster. It is surprisingly easy to come up with MDPs for which DP methods are not practical. So we will see in the next chapter, when we talk about Monte Carlo, other way to solve MDP problems. And when we get to temporal difference methods, we will see even better methods that are, you can use them for solving MDPs that dynamic programming is impossible to apply. So in summary, policy evaluation backups without a max. Okay, so you need to consider all possible actions. You don't have this max operator. Policy improvement, form a greedy policy with respect to the current value function, and since this value function is specified for or is in terms of the neighborhood of the state that you are updating, we say this is a locally update of the values. Policy iteration is in this one you alternate the both two processes, so you need to apply evaluation and improvement. In value iteration, then you back up with a max. Then here you just select the best action and you update the value based on that action. There is a concept called full backups. We didn't talk about this. Full backup means that since you are updating the values of the states, full backup is an update where first you calculate all the new values for every state, and once you have calculated these values, you replace the old values for every state with the new values. In the way I explained this algorithm, or the way it is written, this algorithm, you as soon as you calculate the new value for a state, in that moment you are replacing the value, the old value, with the new value. So in the full backup, what you do is just you keep a temporal memory array where you will be storing all the new values, and once you have calculated all the new values, then you update, you replace the old values with the new values. We talk about the generalized policy iteration, which is this idea of iteratively evaluating the value function and improving the policy, and this is a general idea, general framework to follow. We talk also about asynchronous dynamic programming, which is a way to avoid exhaustive sweeps, so you just update a subset of states each time. And these methods, these dynamic programming methods, are called bootstrap methods, and they are called this way because you perform updates based on other estimates. So you calculate estimates based on other estimates. So remember, you initialize the value function with some random values. In this case we said, okay, make them to be 0, and then every iteration is just an update from an estimation. So that's why this is called bootstrap. In the Monte Carlo methods that we are going to study in the next chapter, we don't bootstrap. We just calculate the estimates from the real output, from the real return of the system. Okay, so I hope this is useful. Thank you, and talk to you later. Bye.